I want to do some examples in degree 4. So we've seen degree 2, which was really trivial, degree 3, which allowed, of course, for the full symmetric group, but we also saw an example where the Galois group was the cyclic, or in this case, alternating subgroup of the full symmetric group. I know I'm getting into group theory here, but if you're not familiar with these terms, just understand that the degree 3 example simply showed how a polynomial can have this extra Galois relation, which gives rise to the Galois group being a proper subgroup of the full symmetric group. Okay, so now degree 4, I'm going to show actually 3 examples: f of x equals x to the 4th plus 1, f of x equals x to the 4th minus 2, and f of x equals x to the 4th minus 10x squared plus 1. And for each one I've written out, again, as we know, we have to specify a given enumeration of the roots of this polynomial. So what I've done here, we have roots that are equally spaced around the unit circle, and here we have roots that are also equally spaced around the unit circle. I didn't draw the picture here, but they are spaced along the real and imaginary axes, and they all have modulus 4th root 2. And then here we have, you can easily verify that these roots are satisfy this polynomial just by multiplying everything out. I've written out the approximate values of the roots. And I've also listed, for each of these polynomials, a set of non-symmetric algebraic relations between the roots. And again, that's a mouthful, so I'm just going to call them Galois relations. And you can see that these relations are, there are different sets of these relations, and of course we could also multiply them and add them and have similar relations, but these are essentially what you might call in abstract algebra lingo the generators of the ideal of non-symmetric algebraic relations. Okay, so let's look at how do we, so given these sets of relations, how do we find the Galois groups? What permutations are allowed to be in the Galois group and which are not? Okay, let's see. Let's start with this one. This one's probably the easiest. So here, we can permute the values R1 and R3, and we still have this relation is unchanged. We can permute R2 and R4, this relation is unchanged. And another thing we can do is we can permute R1 and R2 and also simultaneously permute R3 and R4. Okay, now this is very important because what we need to understand here is the permutations in the Galois group preserve the set of algebraic relations as a set. They don't necessarily preserve every individual relation in the set, but as a set, these relations remain unchanged. So here, what we've done, if we switch R1 and R2 and R3 and R4, then this relation changes, but it changes into one that's already in this other set. So that's okay. However, if we only interchanged R1 and R2, we would end up with R2 plus R3 and R1 plus R4, and those are not in this set. So that is not allowed in the Galois group. So that's very important. So the Galois group is the set of permutations which preserve the set of Galois relations. Okay, here, in this example, we have a somewhat more restricted set of relations that work. Again, we can, well, so here what we have, for example, is R1, R2. Now you might think, okay, we can interchange R1, R2, and we get, this is fine, this is preserved. But then the problem is, if we interchange R1 and R2, now this becomes R2, R4 minus 1, and that is not in the set. So again, you have to look at the entire set. You might be okay, this simple transposition of R1 or R2 might be okay just by looking at this relation, but it's going to change this one to one that's not in the set. So a simple transposition of R1 or R2 is not allowed in this situation. What is allowed is if we interchange, for example, R1 and R3, and then also simultaneously R2 and R4. Let's see how that would work here. Well, if we change R1 to R3 and R2 to R4, we have R3, R4 plus 1, and that's the same as this relation. So there we're good. And you can check that the rest work. So I'm hoping this gives some understanding of what the Galois group is and how it relates to these Galois relations. Final example here is actually, and now this is a little bit interesting to me because you'll see that the sets of relations, this is actually a subset of this set of relations, but the Galois group is the same. By the way, I've written out notations. If you do happen to know something about finite groups, you'll know what these notations mean. This is the dihedral group on a square. This is the what's called the Klein 4 group. Same over here. So these have identical Galois groups, but yet this set of relations is a subset of this set of relations. So we do not have an exact correspondence between Galois groups and sets of algebraic relations, but there is some sort of connection. Okay. Again, I've written out these notations. I don't want to get heavily into group theory right now, but I'm just noting them for future reference. Okay, so this brings me to my conclusion and set of questions for the Worldwide Brain Trust watching this video. So if you take a course in Galois theory, they talk a lot about how to compute Galois groups. And there are various theorems that were discovered, a lot of them in the 19th century, that give you various clues as to the structure of the Galois group. And you can use them to deduce properties and eventually, hopefully, figure out what the Galois group has to be for a given polynomial. Okay. And now, of course, in more recent decades, with the advent of widely available computers, there's been a lot of research done in the area of computer algorithms for, again, finding Galois groups for a given polynomial. Okay. But here's the thing. If you know these algebraic relations for a polynomial, you don't really need specialized theorems, nor do you need a lot of computing power to figure out the Galois group. You simply go through and check which permutations work and which don't. So it seems to me that really the more fundamental question is, what are these Galois relations? Because once you know the Galois relations, it's pretty easy to figure out the Galois group. So why is there all this emphasis on computing the Galois group? And not only that, but as we see right here, the Galois group can be the same for different sets of algebraic relations. So if you want information about these polynomials, if you want to understand the internal structure of these polynomials, what you really want to know is the Galois relations. And the Galois group is just kind of a sideshow. The relations will give you more specific and more in-depth information than the Galois group alone, it seems to me. So why is there this emphasis on the Galois group? And then, I guess the final question then would be, what actually are, now for the third degree polynomials, we saw really the only possibilities were, as we know what the possible Galois groups are for a given polynomial. We know that they have to be, because we've assumed these are irreducible. There's a theorem that says the Galois group has to be what's called a transitive subgroup of the symmetric group. So, and that's pretty easy to enumerate. For degree 3, it's just the full symmetric group, or it's what's called the alternating or cyclic group, subgroup of S3. And that's it. Those are the only two possibilities. And I'm pretty sure the relation that I showed, the example that I showed, pretty much covers the possibilities for degree 3. For degree 4, I don't really know what the possibilities are. Like, what are the possible sets of algebraic relations? We know that for, again, in terms of group theory, the possible Galois groups are S4, A4, D8, V4, and C4. I think that's right. So we know what the possible Galois groups are, but again, that doesn't necessarily specify the Galois relations. So how do we tabulate the possible Galois relations for a fourth degree polynomial? I don't know. I've never seen. Now there is a paper that I think tries to classify quartic polynomials, and I'm going to be. I'll try to find the site for that, and I'm going to be investigating that a little bit more. But it doesn't seem to be easy to find the answer to this. And this to me seems a fairly basic question in the realm of Galois theory, and it doesn't seem to be easy to find the answer. So these are the kinds of questions I find interesting, and this is to me, this hopefully illuminates the main ideas of Galois theory for you. Would be delighted to hear your reactions, comments, questions, and if necessary, insults. That's fine. I'm very thick-skinned, but I'll be happy to hear your reactions and comments, and I appreciate your watching. Thank you very much.